So we will start a new topic today, which is one of the most important topics in OS, which is memory management. Now, let's start with some background. So by memory, we refer to the main memory, which is the RAM, right? So we know that, so all of us, when we write programs, we assume that the data is in the memory. And we have studied this earlier, that a program is usually a file in the disk that has to be brought from the disk and loaded into the memory and placed within a process for it to run. Okay. So the memory is what contains our data as well as our codes. So the processes, different processes running on a machine, they are sharing the memory, and all our data that are accessed by the programs, we think that is in the memory and so on, right? And since multiple programs are or multiple processes are sharing the memory, there needs to be some kind of protection mechanism so that one process does not encroach on the memory of others. So for that, we will talk about multiple schemes for such protection, but an early scheme was using a base and a limit register. So look at the picture. So it's assumed that the memory is being shared by the operating system and several user processes. So usually the norm is that the operating system is in the lower portion of the memory. That means the lower addresses, and the higher addresses are given to different user processes. So for each user process, we can think that we have two registers, a base register which contains the starting address or the part of the memory allocated to this process. The starting address is stored in the base register, and the limit register is the size of the process, the size of the memory allocated to the process. So you see the base and base plus limit, these two values here, they define the portion of the memory which this process can access, right? And when this process is running and it generates an address, the CPU must check whether that access is within this space or within these addresses or not. If not, that means the process is trying to do something illegal, and then we know what kind of thing happens, like a segmentation fault or those kind of things, right? So that is an early scheme. So how will this early scheme work? Let's say this is the idea that, there are different processes in sharing the memory, and each process has a base and a limit register. So now let's say a particular process is executing now on the CPU, and the CPU generates an address while executing that process. So first it is checked whether the address generated by the CPU is greater than the base register value. If not, then this is an illegal memory access, so there is a trap to the operating system. That means an addressing error. If the address is higher than the base register value, then it is checked whether it is lower than the base plus limit register. If not, again addressing error. Only if the address generated by the CPU lies within the value of the base register and the value of base register plus value of limit register, only then is it sent to the memory for access. So this is like one early scheme of ensuring that multiple processes sharing the memory do not encroach on each other. But we will see better schemes as we go ahead. Also, another background point to note, which we have discussed earlier, is that a process can be swapped temporarily out of memory and then brought back again for resumption or execution. This we discussed. If you remember, when discussing process states, we talked about swapped out and so on. So there is usually a backing store, which might be a part of the disk itself, like swap space, which is used for temporary storage of such processes which are swapped out of memory. Right. So maybe there are too many processes trying to share the memory, and it is not possible to fit in all of them at the same point of time in the given memory. So then some of the processes may have to be swapped out to this backing store, right? And later again, when that process has to be run, then it is fetched back again from that backing store to the main memory. Okay. So these are some background things. By the way, just remember this swapping thing. This swapping thing will have a big role to play in what we discuss subsequently. But for now, just keep it at the back of your mind that yeah, sometimes processes are swapped out from the main memory to some backing store, and later maybe when the process is about to be run or something, it can be brought back in, swapped into memory. Also, this means one important point, which again keep this in mind. That means that the total physical memory space of all the running processes can actually exceed the size of the physical memory. Right? So let's say you have a 4 GB RAM, but it might be that all the processes that are currently running, again, take that running word with a pinch of salt. They are not actually running simultaneously because at a one point of time, only one process can run. But like all the processes which are in the system currently, it may be that the total memory of all those processes together actually exceeds your RAM size. And that is possible because some of the processes might be in this backing store. So just remember this will come back later. We will discuss these things in detail later. Okay, but for now, let us keep this aside. Let us not talk about this backing store and all. Let us focus on the main memory itself. So even that has a lot of things to discuss because there are lots of challenges. So all of us write programs. Think that while writing a program, what do we expect or want from the memory? So we inherently assume that the memory addresses will start from 0. Right? So I guess like all of you have been writing programs from first year, even from school, maybe some of you. Have you ever wondered where in the memory will my program be stored? Will it start from memory address 1000.2000? No, we don't want to worry about those things. We want to write a program just thinking that the memory address will start from 0. Right? And we also want that the memory will be contiguous. So we think that, the abstraction that we have is that our memory, the memory that is available to our program will start from 0, 1, 2 and go to a very large number. It will be a contiguous block of memory from 0 to a large number. Also, we want that we should be dynamically able to increase the memory. Right? That is what has been taught to you, say, right in the PDS course, like malloc and calloc. So we can anytime dynamically increase the memory. Also, I should have as much memory as I want. Right? So I would not like to hear that suppose you wrote a program in the computer department server, which has lots of RAM, say 64 GB RAM. Okay. Later you are running the same program on your laptop, which has just 4 GB RAM. You would not like to hear from the operating system, oh, this program cannot run here because we have only 4 GB RAM in this machine. You would not like to hear that. You would say, oh, I don't want to, I don't care. Whatever program I write should be running on a machine with 64 GB RAM as well as on a machine with 4 GB RAM. Right. Also, I should be able to get, like, if I have, like, let's say I have used 32 GB of memory, but I don't want to hear that the RAM of this computer is only 4 GB. Right. So these are some of the things that as a programmer, we expect from the memory or we want from the memory. Also note that you are not the only person running your code on a system. Think of the department server when a lab is going on. Maybe 100 students have logged into the server and all of them are using their programs. Now, all of them will want that their memory address will start from 0. Now, clearly, this is not possible physically. Right, so a memory is a physical device, right? You cannot store 100 programs all starting from memory address 0 physically. So clearly, some mechanisms are needed so that programmers get this kind of view of the memory. That means the programmer does not have to worry about the finer details of where in the memory the program is getting loaded, etc. They can just focus on the program. Considering this abstraction, that memory will start from address 0 and it will be a contiguous chunk up to a very large number. And in fact, that number can be increased dynamically. I can ask for more memory as and when I need it. Right? So this is what the programmers want or expect from the memory. But now, this is not possible physically. Like, as I said, you cannot, in a physical memory, You cannot have multiple programs starting from address 0. So then what needs to be done? That is what we will be discussing in this chapter. If you have any questions in between, feel free to ask. So because of these expectations from users, there comes this technique of address binding. So basically, a user wants to write programs without worrying about where in the memory our program will be loaded during execution. We want to assume that memory address will start from 0. So now multiple users have these expectations and all their programs should run together. Therefore, there needs some mechanism to map the addresses generated by a program to actual physical addresses. Maybe two different programs are currently running, or two different programs are there in the memory now. Both of them, when they run, they will generate addresses considering the memory starts at 0. But clearly, only one of them can be stored at 0. And in fact, none of the user programs are stored at memory address 0. As I said, usually the kernel or the operating system itself occupies the lower address portions of the memory. Okay. So it seems there are two address spaces. One is the address space which the programmer is seeing, or the program is seeing. Another is the physical address space. Right? So it seems there are two address spaces, and address binding is mapping address from one address space to another. And what are those two address spaces called? One is called a logical address space, the other one is called a physical address space. The differences will be clear soon, but just understand the abstraction. So the logical address space is what the programmer sees, or what the program, when executing on the CPU, the addresses that are generated by the program executing on the CPU, those are called logical addresses, or sometimes called virtual addresses. So the logical address space is the set of all logical addresses generated by a program, which starts from 0, right? And physical address is the address actually seen by the hardware memory unit, right? As we will see in a few slides, the logical address space and the physical address space may not be the same. So there is a process by which a logical address generated by the CPU is mapped to a physical address. As I said, like multiple programs are maybe using the memory. And when each of the programs are running, they generate a logical address starting from 0. But it is not possible that the same address is given to both of them physically in the memory. So there has to be some translation, some binding or some mapping from the address generated by the CPU while running a program and the actual address that is sent to the memory device. Okay. So mapping from this logical address space to the physical address space, that is called address binding. So these things will become more clear as we go ahead. So just bear with me for some time. So we have what is called a memory management unit. It's a hardware device that maps virtual to physical addresses at runtime. That is important, at runtime. Okay. So, by the way, just as an aside, let me tell you, I'm not going into details here. So when you write a program and says right from writing a program to actually it being executed, the address mapping happens in multiple stages. Okay, like while writing a program, we just use symbolic addresses like variable a, ampersand a, variable I, and so on. So they have to be mapped to some addresses. So who does the first level of mapping? Any idea? Who does the first level of mapping? So from the symbolic names like A, B, C, these variables to some kind of addresses, who does the first level of mapping? Exactly what Simanth said, the compiler. Okay, the first level of mapping is done by the compiler. But here we are not talking about that mapping. Here we are talking about, say, this mapping which is done by the compiler happens during compile time. We are not talking about that. We are talking about runtime. So your program has been compiled and the a.out file is saved on the disk. Now you are running it. So it has actually been loaded into memory, physical memory, and it is now getting executed. Even then, there is some need of mapping a virtual address or a logical address to a physical address. Okay, we are talking about that mapping. So that mapping is done by this hardware device called memory management unit. So the user program generates logical addresses. The MMU transforms or binds those logical addresses to physical addresses which actually go to the memory. So now we will see in more detail what is going on here. But understand that this concept that there are two different address spaces, logical and physical, and this memory management unit is mapping logical addresses to physical address. Consider a simple scheme. We will consider different schemes of such mapping, but consider the simple scheme. As we discussed, all programs will generate logical addresses, assuming that the memory starts from 0. But that is not the case. We have seen a picture like this picture, let's say. Let me just go back. So this picture here. Okay. See, all programs or all processes do not start from 0. In fact, none of the user processes start from 0. So when a process is running, the CPU is generating addresses, assuming that the memory starts from 0. But actually, in physical memory, these processes are not starting from address 0. So that means someone has to. So suppose the CPU when running a program generates. Say the CPU is running this program, this middle one. Okay, which lies between 300040 and 420940. The CPU is running this program and it generates the address 5. Okay, because it thinks that the memory starts from 0, it generates the address 5. What does that mean? Which memory should it actually be mapped to? So this process, this middle one, and that is being executed on the CPU, it generates an address 5, let's say. But this is assuming that the memory starts from 0. So this address 5, this logical address 5, to which should it be mapped? To what physical address should that be mapped? Yes, any answers? Okay, in the interest of time, let me move on. So basically, this process thinks when running on the CPU, it thinks that the memory address starts from 0. But in physical memory, the address actually of this process starts actually from 300040. So when it generates an address 5, this should be added to this base register, and therefore the address should become 300045. That is what is being discussed here. So we have talked about our base register, but now we change that name, let's say, to a relocation register. So whenever the CPU generates an address, a logical address at 346, the memory management unit knows that this process actually starts from location 14,000 in the main memory. And therefore it adds this value of this register to 346 to get the physical address. So this part is done by the memory. So the CPU generates an address considering a logical address, considering that the memory starts from 0, but that is bound to a physical address by the memory management unit by adding the relocation register. Okay. So different processes will have different values for the relocation register. Right. So that is how, even though different processes when executing on the CPU might generate the same logical address, they will actually get mapped to different locations in the physical memory because we are adding this relocation register to each of them. Right. So by this simple scheme of having a relocation register, by the simple scheme itself, we can satisfy one of the expectations of the programmer that memory addresses will start from 0. So now the programmer can write programs considering that the memory address starts from 0, right? And even the compiler can generate code considering that the memory address will start from 0. However, actually it will be mapped to a physical address later by use of a relocation register. Okay. Okay, so any questions at this point? Okay, if not, let me proceed. So let's go ahead with the second expectation from programmer point of view. That is, the memory will be contiguous. Fine. So let us try to give contiguous memory to every process. Then let's see we will see what are the difficulties with that. So let us go ahead with contiguous memory allocation. So see, just by looking at the picture, you will see that okay, every process will be allocated a contiguous block of memory as much as the process needs. Right? So the lower portion of the memory will be usually the kernel of the OS itself should be, usually is in the lower address portion of the memory, and the higher portion of the memory is initially vacant. As and when new processes come, they get a single contiguous section of memory as much as they need it. So if you see here, initially processes 5, 8, 2 were running, then 8 ended, process 8 ended. That means this empty space was created. This is called a hole. Okay, the hole is the empty space in the memory. And then a new process came, process 9, so it was allocated a part of this hole. Then the hole was a smaller hole. Another process 10 came, the process 10 was allocated again a part of this hole, and so on. Right? So every process is given a contiguous block of memory as much as it wants. Okay. So, and how are the processes separated out from each other physically? By use of a relocation register. So every process, when the operating system knows that starting from which memory address a particular process has been loaded. So it loads that value, starting address value, into the relocation register. And then we use the same technique as we used earlier, that every logical address generated by the CPU will be added to the relocation register. And then it will be checked whether it is inside the limit register. So relocation register plus limit register, it will be checked. And then if yes, then the physical address will be generated to access the memory. So we have discussed this, right? So the MMU maps the logical address dynamically using, let's say, the relocation register. Initially we used the term base register, but now we have started using the term relocation register. The functionality remains the same. The starting address of the memory is contained in that register. And there is a limit register which says what is the total size of the contiguous chunk which this process has been allocated. Okay. So that's the simple contiguous allocation. And clearly different processors can get different sized chunks depending on its requirements. And we use the term hole to indicate a block of available memory. Right? So holes of various, so in this picture, there is a single hole. But actually, if you understand, holes of various sizes can be scattered throughout the memory. So just like here, so the picture that you see here, at this point at the end, processes 5, 9, 10, and 2 are running, and there is a one hole. Now suppose process 5 ends. Okay, so another hole will be created where process 5 currently is. So at any point of time, there can be multiple holes scattered throughout the memory. Okay, and the operating system maintains information about the allocated partitions and the free partitions or holes. The operating system needs to maintain this information because when a new process comes, it has to be allocated a part of one whole, right? So now suppose a new process comes. So there are some free holes, and the OS knows which are the free holes. So it knows the size of each hole and how many holes are there. Now let's say a request comes for size n. So a new process will be loaded into memory, which will require a memory of size n. So this memory of size n has to be allocated from one of the free holes. Which hole should the OS use to allocate this to allocate memory for this new process? There are different techniques. One technique is first fit. So allocate the first hole that is big enough. So actually understand that let's say the OS is maintaining a linked list. Every linked list, every node of the linked list corresponds to one hole. Right? So maybe intuitively the node in the linked list will store the starting address of the hole and the size of the hole. So there is this linked list. The OS is trying to figure out from which hole to give this new process a memory of size n. So first fit is allocate the first hole that is big enough. Just traverse the linked list from the beginning. The first hole the OS finds is big enough of size at least n. It allocates a hole it allocates n bytes memory and allocates it to the new process from that hole. Another strategy is best fit. So allocate the smallest hole that is big enough. Okay. So it actually goes through the whole list and figures out which is the hole which is smallest but big enough to accommodate this process, and it allocates the process from that hole. However, there is the cost associated. Must search the entire list unless the list is ordered by size. Another strategy is worst fit. So allocate the memory from the largest hole. This also must search through the entire list. So in general, first fit and best fit usually works better than worst fit in terms of speed and storage utilization. So I hope you are getting this, how the thing is proceeding. Right? Now I have a question. Do you see any problem with this approach, what we are telling? So we are giving contiguous blocks of memory to every process, and the OS is maintaining the holes in the memory. Whenever a new process comes, a contiguous chunk, and whenever a new process comes and asks for memory of size n, a contiguous chunk of size n is allocated from one of the existing holes. Do you see any potential issue with this arrangement? Okay, Deep has a good answer. Difficult to expand memory. Let's see. Let's go back. Let me go back to that picture. Okay, there are two problems pointed out. Deep and Ashutosh, both answers are good. First, let's understand what Ashutosh said. Okay. So see, it may be that there are multiple holes in the memory. So maybe there is a hole of size 5 MB, another hole of size 10 MB, another hole of size 2 MB. So in total 12 MB is free, 5, 10 and 12. 5, 10 and 2. Now a process comes which asks for 12 MB space. So now there is 12 MB free space, but we cannot allocate this to the process because those 12 MB are not contiguous. There are 3 separate holes of 5 MB, 10 MB and 2 MB. Okay, so even if there is memory enough to accommodate a process, we may not be able to give a process that memory because it's not contiguous. Okay, that was the point which Ashutosh said. Good. Deep has a separate answer, which is also very important. Remember, if we go back one more slide, see, this is what we were telling. What the programmer wants from the memory. This point is also there. Yes, the programmer wants the memory to be contiguous, but this point is also there, that I should be able to dynamically increase the memory. So now think about it. Say in this picture, process 5 says, I want to increase memory. It's impossible, right? Okay, it's not impossible, but it's very difficult. to give 5 some extra memory because there is no hole around it, right? So this is a simple procedure where you are allocating every process a contiguous chunk, but it has these problems. Like I mean, it may lead to wastage of memory because there is enough memory to fit a process, but you are not able to do that. Second is it's very difficult to expand memory. Okay, so good answers. Okay, so the problem which Ashutosh pointed out, that has a technical name, and that is called fragmentation. Okay, so there are two types of fragmentation, external and internal. So external fragmentation is exactly what Ashutosh said. So there is total memory space, I mean total free memory space to satisfy your request, but it is not contiguous. Okay, this is called external fragmentation. Internal fragmentation means allocated memory may be slightly larger than requested memory. So this size difference in memory internal to a partition but is not being used. Let's say 20K was allocated, but the process used only 18K. So 2K is wasted due to internal fragmentation. Okay, some of you might ask, oh, the process said the process might have asked for only 18K. Then why was 20K allocated? Any answers? Or does it even happen? Does it happen like when you are writing C programs that maybe you were allocated a bit more memory than what you asked for? Can it happen? Or does it happen? Okay, so Deep, can you unmute yourself? Alignment padding means?
So like structs may have padding inside though that actually increases the size of the struct to what we expected, and also sometimes extra memory has to be allocated.
Why should there be padding?
So because of alignment, say we have a char and an int, and
Yes.
machine requires that all reads are at multiples of 4. So that means we need an alignment of 4.
Yes. Good.
So alignment of 2, and therefore like we need to like add a padding of 1 after the char.
Right. So yeah, due to different reasons, the OS might actually allocate a bit more space than what the program exactly asks for bookkeeping purposes. Like it's easier to give a few kilobytes here and there rather than maintaining exactly that, oh, 19K should have been used instead of 20K. I mean, usually, uh, I mean, it's more difficult for the OS to keep those accounts than give a bit of extra space. So internal fragmentation is not that much of an issue, but external fragmentation is a big issue. Memory is a very valuable resource. We would not like to have this situation where there is empty space, but we are not able to allocate them to a process because it's not contiguous, right? So, okay, now one thing is there. You might say, external fragmentation can be reduced by compaction. That means shuffle the memory contents to place all free memory together in one large block. So let's say there are 3 holes of 5 KB, 10 KB, and 25 KB, and you move the processes around in the memory so that all these 3 holes come in one side to have a large chunk of free space. That is possible. There's a name for it. People did try it out, compaction, but this is very expensive, right? And I mean, usually avoid it. Okay. And for the same reason, dynamically increasing memory is also very expensive. This is what Deep pointed out. Sure, you might say, oh, move one process a bit, and then you can allocate some extra space to the process which asked for it. But can be done theoretically, but I mean, in practice, very difficult. Right. So we understand that this requirement, memory will be contiguous. In isolation, this is easy to do. I mean, just give a contiguous allocation. But there are problems like fragmentation and wastage of memory. Also, there is a direct collision or a direct mismatch with this requirement that dynamically increase the memory. Right? That is why contiguous allocation is no longer used nowadays. Okay. So again, contiguous allocation is a very simple scheme, and this requirement of, so if you see just with contiguous allocation, we would have So this requirement we have already kind of satisfied with the relocation register concept. Also, with relocation register and contiguous allocation, just like we discussed, we would have satisfied these two constraints, these two expectations. But then this third expectation we would not be able to, in practice, satisfy, right? Also, there are these problems of wastage of memory, right? So we would not like to do that. Therefore, we move towards more complicated schemes of non-contiguous allocation. Right? So let's see how it happens. Remember again, we will henceforth we will discuss non-contiguous allocation, but we want the programmer to get a contiguous view. That means while writing the program, or even when compiler is compiling, we want this abstraction to be there that the memory is contiguous. But actually in physical memory, we will change contiguous allocation to non-contiguous allocation. So now let us see how that proceeds. If you have any questions, feel free to ask. So now if you see the next two topics, segmentation and paging, these are two techniques for non-contiguous allocation. Okay. Actually, paging is the more popular thing. That is what we will discuss in detail. We will briefly discuss segmentation and then go to paging. Okay. So in segmentation, here the effort is to make the memory management scheme similar to how a user views a program. So when we view a program, the user's view of a program, we think of different functions, then maybe a symbol table, different objects, a stack, this kind of things. We in our in our mind when writing a program, we have this kind of segments that okay, these are the memory elements that our program uses. In this scheme of segmentation, we try to map each of these segments into a physical memory chunk. Looks something like this. So suppose the user program has 4 segments. Often the compiler creates these segments, like, we have discussed some abstraction of it, like say the code segment, the heap, then the stack, right? So these are segments, let's say. So these segments as if get mapped to the physical memory, but not non-contiguously. So here the segment 1 is mapped to here. Segment 2 is not contiguous. Segment 2 is mapped here, and so on. So there are 4 segments in the user space or the user's view of the program, and all those 4 segments have been mapped to the physical memory, but in a non-contiguous way. Okay. So if this scheme has an advantage. If we can implement it, it has an advantage that the user space will still look, contiguous. Okay, but physically it won't be contiguous anymore. So now let me ask you a question. If this kind of a scheme has to be implemented, what do you think is needed? Like something like a relocation register, limit register would be enough, or what do you think would be needed? I mean, think from the OS point of view. What kind of data would the OS have to maintain in order to implement this kind of a scheme? Like earlier, we talked about a relocation register and a limit register. Okay, for contiguous allocation, a limit register and a relocation register was enough. But now we are moving to non-contiguous allocation. What do you think the OS will need to maintain? What kind of data will the OS need to maintain in order to implement this? Let me repeat. The user program will continue to think of the memory as contiguous, and it will generate addresses based on that assumption. But physically, the memory allocation is not contiguous anymore. So what is required? Okay, Deep and Vineet have answers. Deep says multiple base and limits, and Vineet says a mapping between them. I would imagine a mapping between the segments, mapping between the segments in the user space and where they are in the physical memory. Yes, both are correct. Basically, multiple base and limits, yes. Basically, it uses a table of segments and bases and limits. This table is called a segment table. So let's understand. Here, the logical address consists of a 2-tuple, a segment number, say S, and an offset within that segment called D. And the OS maintains a segment table for every process, which is used to map a logical address to a physical address. Now the segment table has one entry for each segment of this process. And what does each one entry contain? Like what Deep said, it's a base and limit. So base is the starting physical address where this segment has been loaded in the physical memory, and limit is the specifying the length of the segment. So basically multiple base and limits, one for each segment, that is grouped into a table which we call segment table. Also, there are other fields in a segment table. I'm not going into details. Look up the Galvin book. So there are things like protection bits, access privileges, and so on. We are not discussing those in detail, but we expect you to read the book. But essentially, for every, earlier we had one base and one limit because the whole structure, the whole allocated memory was contiguous. Now we are saying segments can be spread out over the memory. Therefore, for every segment, we need a base and a limit. Right? We are grouping them into a segment table. So this picture would make things clear. So the CPU generates an address, this two tuple, right? Segment number S and offset D. Offset is within the segment, which exact data point do we need to access. Now, that is this segment table being maintained. Every entry of this segment table contains the base address of that segment, the starting address of that segment, and the limit, which is the length of that segment. Okay. There are other fields. For simplicity, they are not shown here, like protection bits, etc., etc. So the way the mapping from this logical address to physical address takes place is as follows. This segment number generated by the CPU is used to choose one entry from this segment table. Okay. So if the segment number is say 4, that means 0, 1, 2, 3, 4. The fifth entry in the segment table wants to be accessed. So usually segment numbers start with 0, right? So you see, if the segment number is a 4, then forget it. So if the segment number is 4, then the entry just after 4 in the segment table want to be accessed. So first a check will happen. So within this segment, the CPU is asking for address D. Is that segment large enough? Maybe if the segment size is itself 1000 and D is 1050, this should not be allowed. So it is checked. Is D less than limit? If no, then an addressing error. If yes, then D is added to the actual physical starting address of that segment, which is stored in this base. Right? Remember, base is the starting physical address of the segment. That is added to D. Base of segment plus D, that gives the physical address which the CPU wants to access. Right? So this is in a segmentation scheme, this is the way of mapping a logical address to a physical address. The segment number is used to consult the segment table. The segment table gives the starting physical address of the segment. And the D is checked with the limit. And then the starting address of the segment is added to D, and that gives the physical address. So this scheme is not, this translation thing, if you remember, is not for a particular segment. It is very similar to what we studied for contiguous allocation. There was this relocation register or a base register and the limit register. Here also the same. The only thing is different segments can be stored in non-contiguous parts of the memory, and therefore for each segment you need a limit and a base register kind of thing. So that is what we call together, like the limit and base registers of all segments together, we call it a segment table. Okay. Any questions? Okay, great. So this scheme worked. There was one small disadvantage, that the different segments can be of different sizes. Okay, so it may happen that the data segment is huge, code segment is small, or the reverse, the code segment is huge, the data segment is small, and so on. And therefore, bookkeeping became a bit difficult. Also, fragmentation issues came up, like the external fragmentation things. Because the segments are of different sizes, it may happen that a process requires a really large segment, but that much memory is available, but you know, different chunks and so on. And therefore, uh, the segmentation scheme did not become that much popular. Rather, a very similar scheme became popular, which is called paging. Right? So that is what we will study in much more detail. If you have understood segmentation, you will see basically the same techniques, but there are, there are some additional things to discuss because paging actually has become popular. Okay, so let's see. So again, we understood contiguous memory allocation would be the simplest, but there are problems like fragmentation and not being able to expand memory. So now we are moving to segmentation and paging. Okay. I hope you understand that just because we have removed the non-contiguous allocation, let me just go back. Since we have removed the non-contiguous allocation, it is possible to give some extra space to this process. Let's say the process suddenly says, I need more dynamically allocated memory. That means I need more of the heap segment. Okay, the heap segment needs a bit more space. Give some more space to the heap segment for this process. Allocate some more space and mark it for use by this process as a heap. Okay, so if we have non-contiguous memory allocation, then it is easier to allow a process to expand the memory. Also, again, understand it very clearly. The process still thinks that the memory is contiguous. Okay, so the segment number can just be 0, 1, 2, 3. So suppose there are 4 segments. The segment numbers are still 0, 1, 2, 3. So the process thinks that it is still contiguous, the memory. But actually, in physical memory, these segments are stored in different places. And that is being managed by using this segment table. So the mapping from these addresses to the physical addresses are being managed by the segment table. Okay. Now, let me just introduce paging. We will go into the details tomorrow, but let me just introduce paging. So in paging, it is quite similar to segmentation, but here we divide the physical memory in advance in fixed size blocks called frames. Okay. So usually, segments can be of different size, but here we say no. It's difficult for accounting purposes to have segments of different sizes. So can we make all segments of same size? That is what we are trying to do, but we won't use the term segment anymore. Rather, we will talk about page and frame. So the physical memory is divided into fixed size blocks called frames. Usually the size of a frame is the power of 2. Say small frames can be 512 bytes, large frame 16 MB. But in a given machine, like it will be fixed, like a particular, the whole memory is divided into fixed size frames. Typical size is 32 KB, 4 MB. And the logical memory is divided into blocks of the same size called pages. So pages and frames are of the same size. And just like we had segments earlier, distributed in the memory, not contiguous, pages of our process can be distributed in the memory. So they can occupy frames which are not contiguous. So here is a picture. So now the logical memory space of the process has 4 pages: page 0, page 1, page 2, page 3. In the physical memory, these pages are stored in 4 different frames, and the frames need not be contiguous, as you see here. Right? And what do we need in order to translate logical addresses to physical addresses? Exactly like what we discussed in the segmentation scheme, we need a page table. So earlier it was called segment table. Now, because this scheme is called paging, we called it a page table. The page table says here that page 0 in the logical memory, that is stored in the frame 1 in the physical memory. Okay, page 0 in the logical memory is stored in frame 1 in the physical memory. Similarly, page 1 in the logical memory is stored in frame 4 of the physical memory, and so on. Okay. So this is exactly similar to what we discussed in the segmentation scheme. Now we have a page table which helps this mapping. So from a logical page to a physical frame. Remember, pages and frames are of the same size. So this page table is used to translate logical to physical addresses. So basically, to run a program, so a program comes, a new process which requires n pages of memory. The OS simply needs to find n free frames and load the programs. And these frames need not be contiguous. Okay. So let me end the class with one question. So what good points are you seeing with this scheme? What good points are you seeing with the scheme? So is this requirement met, that logical addresses start from 0, or from the user's point of view or the programmer's point of view? I will assume that memory start from 0. Is this satisfied? Okay. I hope it is clear that it is satisfied, because you see the logical address still starts from, say, page 0. So basically, the logical address will still start from 0. We will discuss this more detail tomorrow, but in general, the logical address will start from 0. Also, the logical programs view, the logical memory is contiguous. So page 0, page 1, page 2, page 3 are all contiguous. However, the physical allocation is non-contiguous, and that is the mapping is done using this page table. Also, I hope this is becoming clear that in this scheme, it is also easier to expand the memory of a process. Because suppose a process was using these 4 pages, it required another page, right? So if the OS just needs to allocate one free frame to this process, and note that in the page table. So suppose now this process asks for another page. A page 4 will come here. Another entry will be added to the page table. And let's say this frame 5 is given to the process. So another entry will be added to the page table. That logical page 4 is stored in frame 5. And easily the process can expand its space. Okay. So there are several other things to discuss about paging that we will discuss tomorrow. So I'll stop here today. If any questions, then feel free to ask. Okay, Ravi is asking, for each process, do we need to maintain a separate segment table? Okay, you are asking about segment table, but let me answer with page table itself. I hope you understand that the answer here. So yes, so the thing is that for each process, it is necessary to maintain a page table, because page 0 of one process is maybe in frame 1, whereas for a different process, say process B, page 0 might be in frame 2. So yes, for each process, a separate segment table or page table needs to be maintained. So if you are looking for something more, Ravi, you can unmute and ask. Okay, Ravi, unmute yourself and tell me what do you mean?
Yes, sir. So say if two processes are there and they have different segment tables,
Mhm.
then if say one process has given logical address 0 and it has been mapped to some address 2 in the physical address,
Mhm.
and then so the second process has to know that it should not map to 0, right? So it should not map to physical address 2. So it must know that some other process is using it. So how do we know that if there are separate tables in it?
So at one point of time, only one process is executing on the CPU, and the segment table of that process will be used.
Yes, sir. But if another process is again coming into CPU and it runs, then it will not know, right? If that second physical address is being used by some other process.
Oh, no. Wait. Uh, okay, if I understand your question correctly, I mean, see, the process which is running now on the CPU, it is known where I mean, okay, let me understand. The process that is now running on the CPU, it has its page table or its segment table, right? So why are you confused about some other process? So when that other process runs on the CPU, the segment table of that process will be used. I'm not getting the confusion.
Sir, I mean to say that each will have its own segment table.
Mm-hmm.
But say if process A comes into the CPU,
Mm-hmm.
so then say if the segment table has mapped to physical address 2.
Mm-hmm.
So now physical address 2 is being used by process A.
Mm-hmm.
And then say in some time process B has come into the CPU and it has seen 0 in its segment table, and say if it has also 2 in its
No,
uh,
how will it have? Wait. How will it have?
so I
See,
mean that second process will not know whether the physical address 2 is being used or not. So that is my doubt, that
no,
tables has to be
wait.
dynamically changed.
Since we are talking about paging now and that diagram is open, let me answer your question using paging. But I hope that you understand that the answer generalizes to the segmentation also. See here, it is the page table. I mean, so see, the OS knows that frame 1 has been allocated to this process. It won't be allocated to any other process. So in the page table of some other process, it is impossible that the frame number 1 will be stored there also. So the OS knows, right? When OS has allocated these memories to these process. So they had said this is process A. So the OS has allocated frames 1, 3, 4, and 7 for use by process A. That is what is stored in the page table of A. So in some other processor's page table, these frames will not appear.
Yes, sir. Now I got it. So after giving a physical address, then the page table will be computed. Not it will not be pre-computed.
No, no.
I thought.
No. The page table is filled up by, I mean, after the OS allocates some frames to a process, and and that is what I mean. The OS maintains this, so the same frame will not be allocated to multiple processes at the same point of time.
Yes, sir. Understood.
So, is there any other question, or maybe Mainak, if you want to add something, if you are here. Okay, let's end here today. We will continue with paging tomorrow. Thanks, everyone.